Okay, so here are the completed Lewis dot diagrams for each of those following elements. I'd like you just to take this time to double check your answers, just to make sure that you understand the concept. It's kind of fairly simple in order to draw Lewis dot diagram. There's really nothing complex, no simple tricks. Just keep in mind that an electron's going to want to kind of have their own little seat on the bus before they go ahead and pair up. Alright? Again, you wouldn't want to sit with a total stranger either. Now, let's look at ionic bonding. So, an ionic bond is the electrostatic attraction between oppositely charged ions. So, this is essentially everything that we've been doing with our metal and non-metal, or our ionic bonds that we've already been dealing with, our ionic compounds, okay? So most metals have 3 or fewer valence electrons. So they tend to lose these electrons and become positive cations. So this is something that we know. And how we represent this is, so for example, here we have sodium, okay? And sodium is going to go ahead and it's going to lose its electron, and it's going to be represented like this. So you have, again, your elemental symbol. You're going to have brackets around it, and then you're going to show the charge associated with it. So in this case, it is plus, or plus 1, right? So most nonmetals have more than 4 valence electrons. So because of this, they tend to gain electrons and become negative ions or anions. This is, again, all because of the octet rule, right? Our metals are going to lose their electrons because they're trying to satisfy the octet rule. Non-metals are going to try to gain electrons in order to complete the octet rule. Here we're going to deal with oxygen. Okay, so we're going to go ahead and we're drawing our electrons one at a time. They get their own special seat on the bus, and now they have to pair up. Okay, now we have I've got 6 electrons, just like oxygen has 6 valence electrons. And now to represent this as the negative anion that it is, I take my oxygen, right? I know that oxygen here has its 6 electrons. Now it's going to gain 2 more valence electrons. Those are the ones shown here in red, in order to complete its octet, okay? We put the brackets around it and we show the charge, which in this case is 2 negative. Alright? So after ions form, the attraction between the positive charge and the negative charge draws the ions together and it forms an ionic bond. So when drawing electron dot diagrams for ionic compounds, we need to keep in mind that the number of electrons lost by the metal must be equal to the number of electrons gained by the nonmetal. This is why when we write our chemical formulas for these particular equations or these particular formulas, we do the crisscross, right? So this is why we do it. All right. The net charge on the compound must be 0. Okay, this is something that I've said time and time again, and this is why, right? So we're now looking into the reasons why we name compounds and we make the formulas the way that we do, okay? So you may have to have more than one of the metal and or non-metal in order to balance out the charges, okay? This is, again, something that we know already. So we have examples here. We have sodium chloride, okay? That 1 electron on the sodium is going to go and satisfy the octet rule on the chloride, okay? It's going to give me a positively charged sodium and a negatively charged chlorine, and it's going to form NaCl. Now if I look here for magnesium oxide, okay, we've got 2 valence electrons on the magnesium and we've got only 6 on the oxygen, okay? So it gives me Mg2 plus and then O2 negative. Now as you notice, the valence electrons as they come in, they are shown as non-filled in dots, okay? So that's indicating that those weren't originally there. And now we have magnesium oxide. So we're going to have some more examples for you guys in the next video.